Hello, today we are going to discuss the second part of the section uh, trails, paths, and circuits. Um, Last day we discussed the first part of this section. This is 10.1 of your textbook. Since this section is long, I split that into two classes. In the last class, we discussed an example where we learn how to determine subgraphs of a given graph. Now we are moving to a new topic, which is connectedness. Let me read this first. A graph is connected if it is possible to travel from any vertex to any other vertex along a sequence of adjacency edges of the graph. All right, that's if that happens, we call that graph is connected. All right, you should be able to travel between any two vertices. All right, let me draw a small graph here, an arbitrary graph. Okay, so if the graph is connected, you should be able to travel between any two vertices. If you start from here, you should be able to travel like that, travel like this, and stop here. Those are the two vertices of interest. Or you could travel from here to here. So you will be able to travel between any two vertices. Okay, so that graph is connected. So let's say you have another extra point somewhere here, extra vertex somewhere here. Let's say there are two vertices here with an edge. Okay, so let's consider this is one graph. We have one group here, another group there, a group of vertices and edges. Now if you consider traveling from here to here, it is impossible. You could go like that, but from here to there you can't cross. Okay, so that is not connected. So this case, the graph is not connected. Okay, the graph is not connected. All right. The formal definition of connectedness is stated in terms of walks. So we use walks to define connectedness. All right, so let's read this definition. Let G be a graph. Two vertices V and W of G are connected if and only if there is a walk from V to W. All right, so let me read it again. Two vertices V and W of the graph are connected if and only if there is a walk. Okay, keep that in mind. You should be able to find a walk from V to W. The graph G is connected if and only if, given any two vertices V and W in G, there is a walk from V to W. Okay, the same thing that I explained before. So this is the definition of that. All right. If G is connected, you can say there exist vertices V and W in G. Let me read it again. Let me take this out, take that out. Okay. If G is connected, for all vertices V and W in G, there exists a walk from V to W. So I don't know whether you are familiar with these notations. You find these notations in set theory. This notation is one of the notations that I would like to explain a little bit more, so that you read that as for all. Okay, the meaning of that notation is for all. the meaning of that notation is there exist. They exist. All right. You read this as for all vertices V and W, there exists a walk from V to W. That's what I explained before. So this notation, there's another notation I would like to explain. That is if and only if. If you are familiar with this notation since you have done discrete mathematics 1. If and only if means if right side is correct, the left side is correct. If the left side is correct, right side is correct. That means this relationship works both sides. All right. If it is correct here, then it implies this way is correct. Okay. And then if this is correct, and that implies this way is correct too. All right. So that means if and only if. Let's go forward. We have an example. Which of the following graphs are connected? Now what you have to do is you have to find get all the pairs of vertices and then find a walk. If you get any two vertices in this graph, you can find a walk. Okay, so you can find a walk connecting those two vertices. If you get this and that, you can find a walk connecting those vertices. That means this is connected. This is connected. Okay, now let's go to the next problem. Now I take this vertex and I'm going to travel to that vertex. I could go like that, and then I don't have a way of going from here to here because there's no edge. Or maybe I could go down, and again I can go like this. All right, so in this example there are vertices where you can where you are not allowed to travel between. All right, I'm sorry, not F, there should be question mark. Okay, you can travel between vertices, so this is disconnected. Yes. In the next case, I don't know what your answer is. You might be thinking like this is connected, but that's not true. All right, so this graph is confusing. Okay, let me redraw this graph. One thing you have to emphasize here: this edge and that edge are crossing, but there's no vertex here. Okay, this edge, that is also crossing, but there's no vertex here. Okay, since there are no vertices at the intersection, you could do something like this. You could just draw this like that. One edge, another edge, and then you can take the other edge out because there's no vertex at the intersection. So this is V6, V2, V5, V3, V1, V4. All right. All right. So now you can concentrate on this representation, and you see that you won't be able to find a walk from that vertex to this vertex. No path. You can't travel. You won't be able to find a walk. You could go down like this, and from here to here, no way of going. Okay, you can travel between vertices. There are some vertices you can travel between. So this is disconnected. Disconnected. All right. This explained further here, so you can read it. I have already done this problem here, but if you need more explanation, I gave some description here, so you could read that. All right. Then next, go to the lemma. This lemma is important. I will explain why is that. First, I will read that. Some useful facts relating circuits and connectedness are presented in the following lemma. This is lemma 10.1.1. Let G be a graph. There are three conditions. The first thing given here is if G is connected, then any two distinct vertices of G can be connected by a path. Okay. If G is connected means you can travel between any two vertices. Okay, connectedness means that. So let's say this is the given graph to you. So this graph is connected. That means you could there are edges you could travel between any two vertices. Okay, just to choose two distinct vertices, maybe V and W. Then you will be able to find a path between these vertices. Okay, you will be able to find a path between these two vertices. Path means you can't repeat edges or vertices. Path, I gave those definitions. The definition of a walk, definition of a trail, definition of a path, definition of a circuit, and a lot of things I gave you last time. If it's a path, you are not allowed to repeat edges or vertices. Okay, path. No repeated vertices or all right, no repeated edges or vertices. Okay, no repeated vertices or edges. That means a path. So you could find a path from here to here. Let's say V and W are two arbitrary vertices. So you could find the path like this. So this is the path. It happens if the graph is connected. Okay, what happens if the graph is disconnected? If the graph is disconnected, there might be an vertices and edges like this. So you won't be able to go from one. You won't be able to go between all the pairs of vertices. Let's say this is one vertex and the other vertex, so you can go between these two vertices. You could come here, but from here to there, there's no way of going. Okay, so in this case it is disconnected. All right, so let me take that part out. All right, this is connected. Okay, then part B, if vertices V and W are parts of a circuit G and one edge is removed from the circuit, then there exists a trail from V to W in G. Okay, this is what is given here. So you have a graph. Let's say this is the graph given to you. If vertices V and W are parts of a circuit, okay, then you have to remember the definition of a circuit. If it's a circuit, you can repeat edges. No repeated edges. Okay, and then start and end at the same vertex. And start and at the same, okay, start and end at the same vertex. That's called a circuit. Okay, you are not allowed to have repeated edges. Then this says if it's a part of a circuit in G and one edge is removed from the circuit, then there still exists a trail from W to V to W. Let's say this is the corresponding circuit. So this is a circuit. You can see that it doesn't have repeated edges. So this is the circuit. Okay, now you could remove an edge. Okay, you could remove an edge from this circuit. Give me a second. Okay, now that what you do here is you just remove. Let me copy this first of all. Alright, so this is the same circuit. Now what I would do, I'm sorry. Alright. The same thing what I would do is I just remove an edge. Let's say I remove that edge from the circuit. Okay. One edge is removed from the circuit, then there still exists a trail from V to W. Let's say V is, I don't know what is V and what is W, but you can just mark anything as V and W. Let's say this is V and that is W, V and W. So you can see still, even though you don't have this connection, even though you don't have this connection, you can reach to W in that way. Okay, there's a trail. You won't be able to reach in this way. You won't be able to reach in this way. Okay, this way is impossible. You can reach that way. Let me use something else. But going from, give me a second, going from here to here is a question. It's impossible, but still you can just go from V to W if you use the yellow trail. Right, that's given in part B. Part C says if G is connected and G contains a circuit, then an edge of the circuit can be removed without disconnecting G. Okay, this is also a good statement. Let's say you have this graph. G contains a circuit. Let's consider this is your circuit. You can remove an edge from this circuit. You can remove an edge from this circuit. Alright, let me take this above. Now I'm gonna remove an edge from this circuit. So now it doesn't have that edge over there. Now you have already removed an edge from the circuit. The thing is, graph is connected. The graph is connected. It doesn't disconnect the graph. Okay. Why it disconnect the graph? Why it do not disconnect the graph? Because whenever you have a circuit in the graph, you have always two walks to travel between vertices. When you have a circuit like this, when you have a red color circuit like this, there are two ways of going between vertices. Let's say these are the vertices of interest. There are two ways of traveling between these two vertices. One is this way, the other one is that way. Okay, choose two other vertices of interest. Let's say this vertex and that vertex. Again, there are two ways of going between these two vertices. So what happens if you just remove one edge from this graph, but still graph is connected? Why? Because you can just go across the other direction. So if you can walk between vertices, then the graph is connected. Okay, keep that in mind. Circuits are very nice in graphs. Circuits always make sure the graph is connected. All right. So part C is also okay. C okay, B okay, A okay. Now go to the next part. A connected component of a graph is a connected subgraph of the largest possible size. It should be a connected subgraph and it should be large. There are two conditions that should be satisfied. Alright, so this is the definition. Let H is a connected component of a graph G if and only if H is subgraph of G. Alright, H is subgraph. That means subgraph means a subset of G, subset of vertices and edges. And the next condition is G is connected. Alright. Then third condition is no connected subgraph of G has H as a subgraph that contains vertices or edges that are not in G and not in H. Okay, let me explain one by one. First thing says H is subgraph of G. Okay, that means, let's say this is the given graph to you. This is the given graph to you. All right. So this is G. H should be a subgraph of that. Okay, it should be a subgraph of that. Let's say, let me add more edges and make this little bit complicated. Let me make this a little bit complicated. I take this out and I add these. Now this is the graph. It has two parts. This is the graph, and if H is a connected component, it should be a subgraph. Let's say this is your connected component. That is H. Of course, H is a subgraph of G, right? F is a subgraph of G. All right, the part one is that. And then part two, H is connected. Of course, H is connected. You could find a walk between any two vertices in H. So H is connected. Part 3, no connected subgraph of G has H as a subgraph and contain vertices that are not in H. That means the third condition explains whether this is the largest possible size. Okay, here you saw that is a connected subgraph that is the largest. That is the largest. This third condition assures the connected component is the largest. So this assures the connected component is the largest. Compo is right. H is the largest possible size. All right. So these are the three conditions that you have to satisfy in order to show H is a connected component. All right, let's move to the next one where we can learn an example. Example 10.1.5. Find all connected components of the following graph G. All right, you have to find all the connected components. So the first thing is they should be subgraphs, and then those subgraphs should be connected, and then those subgraphs are the largest connected piece within the subgraph. All right, so how many subgraphs that you can find? For this case, you can find plenty of subgraphs. Okay, you could find plenty of subgraphs, and then those subgraphs should be connected. So if I could choose, let's say whether you like my choice here. So I choose this as H1, my first subgraph, and then this as H2 and that as H3. So I have chosen three subgraphs. Alright, I have chosen three subgraphs. Now, I have to check whether these are the biggest within the subgraph. That's true. If you just consider H1 is the biggest within the subgraph. So you can't add more. You can't add more vertices or edges to H1 to make it bigger. Okay, so you can't add more. You can't add that. You can't add V4 to H1. If you add V4 to H1, it won't be connected anymore. Okay, if you add that to this, it won't be connected anymore. So H1 is the biggest within that connected component, that cluster. Okay, so now just go to H3. If you just consider H3, you can't add more vertices or edges to H3 to make it bigger. So that is the biggest that you could think. If you want to add something to H3, you have to think of adding V4 or some vertices and edges from this cluster. Okay, in any case, you are just making H3 disconnected. So that means you are violating that condition, the second condition. So these are the, let me just take this out. All right, so these are the three connected components for this graph. Okay, so the connected components are H1, H2 and H3. Okay, let me write everything here so you can just read this whenever you need to prepare for exams. G has three connected components. Connect. Okay, I denote those as H1, H2 and H3. With vertex set V1, V2, V3 and edge set E1, E2, E3. Okay, so let me write these edge sets and vertex set. The first edge set V1 is for the subgraph H1. So the vertices are V1, V2 and V3. And then V2 should be actually these are uppercase V, so I have to use different letters, otherwise you will be confused. Or I will make these V's different. So I will write those V's like this. No, uppercase V's. V1, V2, V3. I mark uppercase letters like this. V1, V2 and V3. So the third subgraph has the vertices V5, V6, V7, V8. Okay, these are the vertices, vertex sets. And then we have to write the edge sets. The edge sets are E1. In the first graph you have E1, E2. And in the second connected component, there's no edges, so you just mark like that. That is an empty set. empty set. That means no elements. And E3 has E3, E4 and E5. Okay, these are the vertex sets and edge sets. All right, let's move to the next slide. Now we are going to discuss something very important. In the beginning of this section, I introduce you Euler circuits. If you can remember, I just explained you a map that I copied here. You know, this is the city Koenigsberg in Russia, and it has this river. The city has this river at the middle. What happened here is this river makes four land areas, land area A, land area B, land area C, and land area D, and there are 7 bridges. The problem was you have to start from one land area and come back to the same land area by visiting every land area one time and going across each bridge at one time. Okay, so this was the problem given at the beginning of this section. Now we are coming back to that problem because here we are going to learn Euler circuits and then find the solution for this practical problem. Let me read this first. Now we return to consider general problems similar to the puzzle of the Koenigsberg Bridge. The following definition is made in honor of Leonhard Euler. Okay, you know Leonhard Euler, who's the person solved this Koenigsberg Bridge problem. Okay, first of all, let's learn what are Euler circuits. Let G be a graph. An Euler circuit for G is a circuit that contains every vertex and every edge of G. That is, an Euler circuit for G is a sequence of adjacency vertices and edges in G that has at least one edge, starts and ends at the same vertex, uses every vertex of G at least once, and uses every edge of G exactly once. Okay, this is exactly the problem given in the Koenigsberg Bridge. All right. So Euler circuit is a structure like that. Euler circuit. So in this problem, you have to find a Euler circuit. Okay, that's a special entity in graph theory. Euler circuit. If you could find an Euler circuit here, that means you can just solve this problem. All right. So if you read the Euler circuit, you could understand that Euler circuit is sequence of adjacency vertices and edges in G that has at least one edge, start and ends at the same vertex. All right, uses every vertex of G at least once, and uses every edge of G exactly once. Okay, that means let's say you are starting from here. Okay, you have to use every edge of G exactly once. That means if you cross this bridge, you can't use that bridge anymore. And then you have to touch all the landmass. You can go like that, go like that, maybe go like that, go like that, go like that, go like that. Now you stuck. Okay, you stuck at B. You can come back to A. So that doesn't work. Again, maybe start from A. Maybe go like that, and like that. You stuck again here. So you won't be able to go back to A. So this is what you have to find is a Euler circuit. You pass every edge exactly once, but you are allowed to pass through vertex several times. But of course, you have to visit every vertex at once, at least one time. You have to visit every vertex at least one time. Okay, that's called an Euler circuit. Okay, which is related to this Koenigsberg map. All right. Now go back to the next slide. Let me draw the corresponding graph here. As you remember, the graph was like this. So this was the land area A, this was land area B, this was land area C, and this was land area, this was land area D, and this was land area C. Now if there's a bridge, you can just connect those vertices by an edge. There's a bridge between A and B. There are two bridges between A and B. So you connect like that. There are two bridges between B and D. And then there's an edge between B and C. There's an edge between D and C. There's an edge between A and C. Okay, so this is the corresponding graph. All right, now we're going to find Euler circuits. Okay. For that, we could get use of theorem 10.1.2. If a graph has Euler circuit, then every vertex of the graph has positive even degree. Every vertex should have positive even degree. Okay, so let's write the degrees of these vertices. Okay, here the degree is degree of A is 3, degree of B is 5, degree of D is 3, degree of C is 3. Okay, this is odd, 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 odd. All are odd. Okay, all degrees are odd. All the degrees are odd. All right. If a graph has an Euler circuit, then every vertex of the graph should have positive even degree. But unfortunately, all have an odd degree. So then there's no Euler circuit. Okay, there's no Euler circuit. Before going to that conclusion, let me give you a contrapositive version of theorem 10.1.2. Since you have learned discrete math 1, you can understand this. There are different ways of proving things, and there are different formats of giving theorems. This theorem 10.1.2, explains a forward relation. That means it starts with if. If this is true, then that will happen. Okay, so that's what you have to understand. If this given condition is true, then that cause will happen. Okay. If A is true, then B is true. So that is similar to give me a second. That is similar to theorem number 10.1.2. If A is true, then B is true. That means A implies B. Okay. Then what is the opposite of that? When I say like this, some students might think opposite of this is B implies A. No, that is not true. This is not the opposite. Okay, the opposite is not B implies not A. That is the opposite. Okay, so this is the opposite, which is called contrapositive. Let me get some space here. I'm sorry. Okay, contrapositive is the opposite. This which is given right here. That what the opposite of theorem 10.1.2? If some vertex of the graph has odd degree, that means if this is not true, then the graph does not have Euler circuit. That means if this is not true, then that is not true. All right. If this is not true, that is not true. Not B implies not A. All right, so keep that in mind. You have learned this in discrete math 1. All right, so you could use the contrapositiveness to prove that Kreuzberg map doesn't have Euler circuits. Okay, see, all are odd here. All the values, all the degrees are odd. So then the conclusion is no Euler circuit. Okay, that means no Euler circuit. Thus, the graph does not have Euler circuits. Okay, that means let me write like traveling as explained in the that map is, or let me write like Königsberg bridge problem. That means I have to just check the spelling of Königsberg. Königsberg. That means Königsberg Bridge problem is not solvable. All right, so now you have the solution for the practical example that we discussed in the very first day of this section. All right, there's another example. Let's discuss this example. Show that the graph below does not have an Euler circuit. Okay, you have to show that no Euler circuits exist. Okay, just find out the degrees of this graph. Okay, here for this vertex there are 4 edges, so the degree is 4 here, and there are 3 edges, degrees 3, 1 2 3 4 4 degrees 3. Okay, so those are the degrees of this graph. Degree of V1 is 3, degree of V2 should be 4, degree of V3 should be 3, degree of V4 should be 4. Okay, so those are the degrees. All right, let me check whether there's an Euler circuit. The answer is no Euler circuit. Okay, no Euler circuit, because this is odd and that is odd. If it has odd degrees, then no Euler circuit. That is given in the contrapositive version of the theorem. If some vertex of a graph has odd degree, then the graph does not have Euler circuits. All right, let me write something here. Vertices V1 and V3 both have degree 3 which is odd. Hence, by the contrapositive of theorem 10.1.2, by the contrapositive form of theorem 10.1.2, this graph does not have an Euler circuit. Okay, so that is the answer. Now we go forward. Now we are moving to a theorem 10.1.3. 10.1.3 says if G is connected and the degree of every vertex of G is positive even integer, then G has an Euler circuit. Okay. This theorem is this contrapositiveness explains the not case, as I explained you. Not case means if no even degree, that means if it has odd degree, then no Euler circuits. That is the contrapositiveness of the theorem 10.1.2. Now you have the original theorem as 10.1.3. It says If G is connected and the degree of the every vertex of G is positive even integer, then G has an Euler circuit. Okay, so that is theorem number 10.1, 1.3. Those theorems are more likely similar. Some theorem explains forward direction, the other theorem might explain the reverse direction. Okay, so you can understand that. Now this is the algorithm to find Euler circuits. First I will explain the algorithm and then I will discuss one problem. Since there are computer science students in this class, you can easily code this. This is a very easy algorithm. Of course, this algorithm is available online, written in different languages. The step one of the algorithm is first pick a vertex to the start vertex. That means you for the given network or for the given graph, you just pick a vertex as the start vertex. Okay, and then find at random a cycle that begins and ends at the starting vertex. Okay, so you find a cycle that starts and ends at the start vertex. Mark all the edges of this cycle. This is now your current circuit. Okay, so let me go to the example and then explain you this. Okay, so this is the given graph to you. Now you have to find Euler circuit of this graph. You have to find an Euler circuit of this graph. So you have to start from any vertex in this graph. All right. So before going to start with any vertex, you have to make sure that this graph has Euler circuit or not. How do you find it out? For that you could check the degrees of the graph. You could check the degrees of the graph. Okay, if you just come here, the degree of this vertex is 2 because there are two incident edges. Here degrees again 2, here degrees 2, here degrees 4, here degrees 4, here degrees 2, degree 2, degree 4, degree 2, degree 2. All right. Degree of A, B, C, F, G, I, J are of degree 2 and D, E, H are degree 4. So all are even degrees. Okay, so all are even degrees. That means the conclusion is it has an Euler circuit. So the first step is, first thing is to check whether it has an Euler circuit. So you confirm that it has an Euler circuit. Now you could use this algorithm to find Euler circuits. Okay, let me explain how to use that algorithm. Step number one is first pick a vertex to the start vertex. Actually, there's a small grammar mistake here. Rather say in 2, I could say something like to be the start vertex, so as the start vertex. So let me just correct that. I just erase that and then write like as. Okay, as the start vertex. So you could choose any vertex as the start vertex. Here I will choose I choose A as the start vertex. Okay, this is the start vertex. Start. A is the start vertex, so you start from here and then go to step number 2. Find at random, find at random a cycle that begins and ends at the start vertex. Mark all edges on this cycle. This is now your current circuit. So you have to find a cycle starting from that vertex. So what I would do, I will find the circuit like this. I will go down like that, down like that, any circuit you would like, okay, down like that, and then you have to come back to the same vertex, okay, otherwise it won't be a cycle. Okay, now, so this is your cycle, this is your cycle. Give me a second. Now it should be, so this is the cycle you have. It is A, B, C, D, A. All right. Now you denote that as C. Okay, so that's great. So this is your current Euler circuit. That's your current Euler circuit. Then you have to move to the step number 3. If there is not a vertex on the current circuit that is incident and unmarked edge, you are done. Okay, there's no vertex on the current circuit that is incident to an unmarked edge. All right, so now go back here. So that's not true here. Why that's not true? You can see these two edges are incident to that vertex. So you have to move to the step 3. Have to move to step 3. Now you have to move to step 3 because there are edges incident to the vertex D, which is in the previous cycle. Okay, then okay, now go to the algorithm back. Okay, now if there is such a vertex, find a random cycle using unmarked edges that begins and ends at this vertex. This vertex means the vertex that is described right here. This vertex means the vertex described right here. Okay, this is that, this means that. Okay, the vertex that is incident with edges. So you have to mark, you have to find another cycle. Now go back. So this is the corresponding vertex. Now you have to find a cycle starting and ending at that vertex. So in new case, you go like this, start from here. This part is already done. This part is already done in the previous step. Now you could go like this, from here to there, 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 and come back here. Okay, now this is your new cycle. So the new cycle is actually the summation of this cycle plus that cycle. Okay, now it is C prime. Let me mark C prime maybe in different color. No, you can just understand that. I don't need to use a different color. It is given here. So this is C prime, which is D, E, G, H, J, I, D. Okay. Now what you have to patch C prime into C to obtain C double prime. Okay, C double prime is the latest cycle. That is the latest cycle. Oh, that's bad spelling. Okay, that's the latest cycle. Alright, now go forward. Now do the same steps again. Now you can see this edge is adjacent to that vertex and this edge is adjacent to that vertex. So you can't stop the algorithm. So you have to go to the next step. Next step is you have to find another cycle. Okay, so another cycle is starting and ending at this vertex. Okay, let me clear this for now. So let's consider this is the vertex that I'm interested of, and now you have to just find a new cycle. So you go like that, go like this, come like that. Okay, so now you patch this cycle into the previous Euler circuit. All right. Now once you patch this one into the previous Euler circuit, you get this as the latest circuit. Here I give as give me a second. All right, so this is the new case. It is that thing which is marked right here. All right, now you combine this thing into the previous cycle you obtained, which is right here, which is A, B, C, D, E, G, H, J, I, D, A. So you add that with this and obtain this thing. Okay, so good. So now you can see you covered all the edges. Now go back to the algorithm. Now you ended up here. Now you ended up here. If there's no vertex on the current circuit that is incident to unmarked edge, then you are done. Okay, now once you are here, you don't see any other edges in this graph which is unmarked by an arrow. That means you have used all the edges in this graph. So the process is over. That means this longest path is your Euler circuit. Okay, that's how you find Euler circuits. All right, so let's move to the next slide. Now we are going to learn a little bit more about this Euler approach. The next is a definition where we learn Euler trails, which is somewhat similar to the Euler circuits. Let G be a graph and let VW be two distinct vertices of G. An Euler trail from V to W is a sequence of adjacent edges and vertices that starts at V and ends at W, passes through every vertex of G. Okay, passes through every vertex of G at least once and traverses every edge of G exactly once. Okay, this is also similar to Euler circuit. In Euler circuit, you have to come back to the same vertex, but here you do not need to come back to the same vertex. So that's the difference between this approach and the previous approach. In the previous approach was Euler circuit, where you have to come back to the same place. This is an Euler trail, but you don't need to come back to the same place. All right, so let's learn this corollary. Let G be a graph and let V and W be two distinct vertices of G. There is an Euler trail from V to W if and only if G is connected. The first condition, the G should be connected, and V and W have odd degrees. Condition number 2, and all the other vertices of G have positive even degree. So these are what you have to show. Okay, these are what you have to show in order to show it has an Euler trail. Okay, this is what you have to show in order to show that it has an Euler trail. Okay, so now you have an example here. The floor plan shows below is for a house that is open for public viewing. Is it possible to find a trail that starts in room A, ends in room B? Start, end. And pass through every interior doorway of the house exactly once. That means this is like the Koenigsberg bridge problem. You have to pass these doors exactly once. Pass each door exactly once. All right. So that's what you have to do now, right? Okay. So you have to here what you have to find is a Euler trail. Okay, you have to find a trail. All right. So first of all, you have to put this into a graph. You have to put this into a graph. You could take these A, B, C, D, E, F, G, H, R as vertices. Okay, you could consider these as vertices. Okay, and these are edges. Doorways are edges. If there's a doorway between two rooms, then you can just put an edge for that, right? So you have A here, and there's G. That means there's a doorway between A and G, so you can put an edge. And then here you have H. There's an edge between G and H, so there's a door between G and H, so you can put an edge. And then there's a door between F and H, so you could put an edge. And then H to I, there's a door, H to I. And then H to E, and so on. All right, now it's easy. You can just convert this one into a graph like this. You could just make this graph. Okay, you can just make this graph. Once you have this graph, you have to find an Euler trail. All right, you have to find an Euler trail. For that, you could use the previous theorem. Okay, you could use the previous theorem. Give me a second. The previous theorem says it's the corollary, which says it should be connected. Part 1 connected. Start and end should have odd degrees, and then all the other vertices should have even degrees. All right. So let's check these 3 conditions. Okay. So this is connected, no doubt about that. This graph is connected. Connected means you can travel between any two vertices. You can just walk between any two vertices. Okay, so let me mark that. Number 1, connected. Number 2, the degree of this one is 1. degree of B1 is 1. Those are odd degrees. Alright, so that means degree of, let me write degree. Degrees of start and end of the vertices are odd. Okay, and then third, check the degrees of the other vertices. Here the degree is 2. Okay, there are 2 edges, and 1 2 3 4, here 4, here 1 2 1 2 1 2 1 2 1 2 1 2. Okay, all the other vertices are having degree 2. I'm sorry, all the other vertices are having degree, having even degree. All the other vertices have even degrees. Okay, then by corollary 10.1.5, there's an Euler trail from A to B. Okay, there's an Euler trail from A to B. So you could find the Euler trail. Just start from A, and then you have to travel from A to G, G to H, and then H to this, that to that, that to this, that, 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 and finally this. Alright. This is how you could travel between A and B. Alright. So this has a Euler trail. That means you could start from room A, and then you can end at room B while visiting each door at once, and visiting each room at least one time. Alright, so this is the solution for this example. So actually this is the end of the section. So thank you very much. If you have doubts regarding this section, I'm available online during your class time. You can just jump into Office servers using the WebEx link and then discuss with me. Thank you very much.